Alright gang, here we go. This is for physics. We're doing in Unit 9, Part 2. We're talking about electric fields in this video today. This stuff is a little confusing, kind of different, but also kind of very similar to gravitational fields. So we're going to be referring to gravitational fields quite a bit in this video. Alright, so first I just want to recap kind of a bit about what we talked about in the previous video. Looking at this guy here, it says we've got these three charges, and the bottom two charges are fixed in place. Alright, so these two bottom guys aren't going to move. One's negative 0.6 microcoulombs, and the other one's 1 microcoulomb. And then we take this top charge and we put it right here. We want to know when it's initially put there, in what direction would the net electric force on the top on this top value be pointing? Where would it be pointing? So we know that whenever we have electric forces, okay, if they're opposite charges, they're attractive forces, and if they're the same charge, if they're like charges, then they repel each other. So if we put this positive charge right here, all right, between this positive and the negative, this would be an attractive force. So we know we've got one force that does something like this, and we could label this, F1 or something. And then we've got another force from this guy here, all right, between this particle and this particle here. And so the force of this one on this top one here would be a repulsive force, because they're like charges, and so it would be repulsed in the same direction it's pointing, and it would be up here. Now, as far as the length of these, we don't really quite know until we actually do the math and figure it out, but that's not what the question asks. And we could do it, just use a little bit of, our Coulomb's law and stuff like that, and it wouldn't be too hard to do. But what we want to do instead is we just want to know what direction to be pointing. All right, so we know that in order to get two vectors and be able to figure out the resultant between these two vectors, we just have to add them together. In order to add vectors, we just go tip to tail. So we're going to slide this F2 vector down and add it to the tip of this one. So it's going to come up here, and I'm doing my best to make this parallel. And there's our F2. Okay, so our resultant vector starts at the tip. And really they start over here. But anyway, so they start at the tail of the first one, end at the tip of the second one. All right, so this guy right here, that guy would be our resultant vector, or our net. All right, our net force but would be going down here. So according to the vectors we drew, it would be down here to the left. And then obviously, depending on what the actual length of these two vectors would be, the force would be somewhere amongst here. Now so on and so forth. So we could also take this same idea. So let's erase some of these lines. All right, we'll erase everything but the net force here. All right, we'll erase that, and we got all this gone. So that net force would be pointing off this direction. So, and we could also say, well, what if we have move our charge? Okay, we grab our charge and we move it over here. What would be the net force acting on the charge over here? Well, again, we know we've got a charge that its attractive force would be going down here, and we'd also have a repulsive force going up here. All right, so again, we just add those two guys together, and what would be the net force? Well, our net force would be somewhere over here. And we could put another charge over here, and we'd be like, well, what would happen? We'd have some charge pulling us to the left by this attractive force, but we'd also have a repulsive force. In this specific case, the repulsive force would be stronger for two reasons. Number one, that force is strong, or that charge is bigger than this charge, and more importantly, it's a lot closer. And so, because last video we saw that the closer you are, the more charge or the more force it'll apply, and so therefore, our resultant force would be somewhere this way. All right. In order to calculate that, watch the previous video about Coulomb's law. All right. And so, as we can see, we can put this charge anywhere here, and no matter where we put that charge, we'll have some force acting on it. Now, if you remember way back to like Unit 2 or 1, I can't quite remember, when we first talked about forces, we talked about how there were two main types of forces. We talked about how there were contact forces, okay, and then field forces. All right, contact or field forces. All right, now contact force is a force that involves actual physical contact. Okay, so if you're out playing baseball, it's about that time of the year right now, and so if you're out there playing baseball and you hit a baseball, all right, you're actually applying a contact force in order to move that ball, and that makes sense. And then a field force, though, is something that does not require contact, right? Just being in the vicinity causes that force. It's okay, so being nearby, all right, would cause that force to occur. So we've learned about two specific field forces so far. We've talked about gravity at length, Okay, many of our beginning units were all about gravity. We talked a lot about gravity. And then we also have briefly talked about magnetism. Our next unit will dive deep into magnetism and stuff. But both of those are field forces. This is called the electric field. All right, so around these particles are this electric field. It's causing this electric force that can act upon other charges that get put in place around it. All right, so that's your electric field. So this idea of the electric fields are a vector. Okay, so because they are a vector, they have a magnitude and a direction. All right. Now the magnitude is easily calculated. This is just the magnitude. This is how we calculate the magnitude of the electric field right here. All right. It's the F force on the electric. So in order to calculate that, we just use Coulomb's law over Q naught. Now Q naught's kind of this interesting guy. Let's look at Q naught. Q naught is known as a test charge. Okay, is the test charge. All right. Now test charges are always positive. This is very important. Never forget this. Always positive. All right. Test charges are always positive. Very, very important. Do not forget. All right. So the test charge is a very, very small positive charge, and we're going to refer back to this test charge several times over the course of our learning about electric fields. All right, so the magnitude is easy to find. Now the direction, though, can be slightly confusing, and so in order to determine the direction, we kind of talked about this before in the Coulomb's law video. We established that a negative force is always attractive and a positive force is always repulsive. All right, so same kind of thing works here. All right, now specifically with a test charge is always positive, and our electric field is defined by how a positive test charge would act if we put it nearby that point charge. So we've got this charge right here, this positive charged object, and we're putting this test charge next to it, just right next to it here. All right, we put this test charge down. What would happen? Well, this would be a repulsive force between these because they're both positive. So this test charge would move to the right. So because of that, this electric field points to the right. All right, so and we would define this as a positive electric field. All right, now this guy here, a test charge goes to the left. All right, and so this would be defined as negative because this would be attractive. All right, so this uses the same sort of idea as what we established yesterday. All right, or not yesterday, in the previous video. All right, yeah. Okay, so a little bit more about your test charges. Okay, test charges are always small charges because we want to make sure that they do not significantly affect the field that we're trying to measure. If they're too big, then they'll change the field on their own because we know anything that has a charge has its own magnetic or electric field. Now, because this test charge is super, super small, okay, it's going to have a really, really tiny electric field. Okay, so it's not going to affect. This guy would have a big electric field. All right, so our test charge would always be small enough that it won't affect the electric field. All right, that's the important guy here. Oops. All right, now let's do something else real quick. All right, if we have if we take our electric field that we just established, and we know that in order to calculate this is equal to E is equal to our force of our electric divided by our test charge, or divided by the Q naught. All right, the charge on this Q naught. Okay, now we also know from Coulomb's law that Fe is equal to Kc, which is Coulomb's constant, 8.99 times 10 to the 9th, times Q1, Q2 over R squared. Okay, now let's think about this, and we could take this value here and we could plug this in because these are both Fe's, so let's throw that in there. So it would be Kc times Q1, Q2 over R squared, and this whole thing would be divided by our Q naught. Now let's think about this guy real quick. All right, now in the electric field, right, in this force, we're thinking about these two Q's. And we've got these two Q's here. We've got one that's the positive, and then the other one could be our other positive, whatever. And so let's just think about what's going on here. One of these Q's is this guy, one of these Q's is this guy. There's no reason that this second Q could not be defined as Q naught. So really we could choose to define this guy here as Q naught. All right, and if we do that, and there's no reason why we can't, then both of these charges would be exactly the same. All right, and because they're the same and we're taking this one divided by itself, they cancel each other out, just like in algebra. And so we get a second equation to calculate the electric field. All right, it would be Kc times Q over R squared. All right, and this Q would be the point charge. All right, so the non-test charge. All right, so we get this equation here. All right, and so we're taking Coulomb's law and the thing, and we just derived it together, so we get this thing here. All right, again, our Kc value here, and let's just write that down here. Kc is equal to 8.99 times 10 to the 9th. All right, and it's got funky units. It's like newtons times meters squared over something. I don't quite remember, to tell you the truth. It's got a lot of units. All right, and then Q is our charge. Remember, charge is always in coulombs, and then our distance always needs to be in meters. All right, the SI unit for an electric field is newtons per coulomb. All right, so by using this equation, so now we've got two equations, right? We've got this one here, and then we've also got Fe over Q naught. I'm going to erase it. Fe over Q naught. All right. So we've got both these equations that we can use interchangeably to help us solve problems. So let's try one right quick. It says an electric field around a charged object is 5.95 times 10 to the 6 Newton coulombs at a distance of 0.1. Find the charge on the object. All right. So we've got our electric field, and they're giving us a distance. We want to find the charge on the object. Well, the one that has that value here, that equation, would be this one, because we want to find that charge. All right. So our E is equal to Kc times Q over R squared. We want to find charge. Let's just find the charge. So we'll rearrange this to find Q. So Q would be equal to, and we're going to multiply by R squared, divide by Kc, so we get R squared times E over Kc. All right, our R value, make sure everything's in the right units. All right, it's in meters, so that's good. So 0.100 squared. And then our E value, this was an E, it looks kind of like an F, but there's our E. All right, and our E is our electric field, and so that's just that guy right there. So the 5.95 times 10 to the 6th, all right, Newton coulombs, and then we're going to divide that by our Kc value, 8.99 times 10 to the 9th. All right, so we get 0.1 squared times 5.95 e to the 6th divided by 8.99 e to the 9th. We get how many sig figs do we want? We want 3 sig figs, so 6.62 times 10 to the minus 6th. 6.62 times 10 to the minus 6th. And the units on this would be coulombs, because it's a charge. And I remember that because charge and coulombs both start with the same letter. All right, so there's that, and we could change it to microcoulombs, just dividing by 10 to the 8, or become 6.62 microcoulombs. All right. Now it says, suppose a small test charge of 0.2 microcoulombs was placed at the point that is 0.1 meters from the charged object. What force would be exerted on the test charge and on the object? Well, we can use our other formula for E, right? So we got E is equal to Fe over Q naught, all right? So all we have to do is we have to solve for the force. So that means our Fe, okay, would be equal to E times Q naught, right? And our E value here is the same one as up above. It'd be 5.95 times 10 to the minus 6th. And then our Q naught is the value they give us right there. All right, 0.2 times 10 to the minus 6th. So we get 5.95 e to the minus 6th times 0.2 e to the minus 6th. Oh, it's a positive 6. I'm sure you guys are yelling at your screen. This is a positive 6 there. All right, so let's try this again. 5.95 e to the 6th times 0.2 e to the minus 6th. There we go. And so we get 1.193 sig figs, so it's already there. That's cool. 1.19, and this is force, so this would be newtons, and then we have to define whether or not it's attractive or repulsive. Okay, so so let's think about this. So we started with this guy here is this charge that we calculated earlier is positive. There's our charge from before, the 6.62. And then here's our charge of our test charge. So they're both positive. So this would be repulsive. Okay, so a repulsive force. All right. Let's do another practice problem here. All right, it says a charge Q1 is equal to 4.50 microcoulombs and experiences an attractive force of 1.35 newtons at a distance of 0.15 meters from a charged object, Q2. Find the strength of the electric field due to Q2 at the distance of 0.150. So the easiest thing, this can be kind of confusing, so just start drawing stuff out. All right, so Q1, it says we've got one charge, and it says it's positive, right? It's a positive 4.50, so there's our positive, and we're going to say this is our Q1, and our Q1 is equal to 4.5 times 10 to the minus 6 coulombs. All right. And it says that it experiences an attractive force of 1.35 newtons. So it's going to be some force of 1.35 newtons. It's going to be pulling us towards this other charge. Now, because it's an attractive force, we know this other charge has to be negative. All right, so we can go ahead and mark that as negative. And we'll name this guy as Q2. All right, and then finally it tells us that the distance between these two guys here is 0.150 meters. All right, and it says find the strength of the electric field due to Q2 at a distance of 0.150 meters from Q2. All right, so what can we do to solve this? Well, we've got two formulas to find our Q, or our electric field. All right, so our E, okay, would be equal to, and so in this case, because we know here the force and this charge here, we can just use the first one, right? That'd be the easiest one to use. So our Fe over Q naught, all right? Okay, so our Fe value is 1.35, and then our Q naught was the 4.5 times 10 to the minus 6th. All right, so we take our 1.35 divided by 4.5 e to the minus 6th, and we get 300,000. Right, now let's think about, what would it be? It's an attractive force, so that means it would be negative, right? And so we should have probably established this in negative, so it would be 3 sig figs, so 3.00 times 10 to the 300,000, so fifth. And then it's an electric field, so it would be newtons per coulomb. And that makes sense because this was in newtons and this was in coulombs. All right, so there's the strength of the electric field due to Q2 at that distance. All right, then we have this final question here. It says find the charge of Q2. All right, well, this isn't too bad. This is very similar to the question we just did, all right, a couple of slides ago. All right, we know that our electric field is equal to Kc times Q over R squared. All right, and now we have our electric field, and we want to find Q, so that means our Q value would be equal to R squared E over Kc. All right, so our R squared value here would be 0.15 squared, and our E value is what we just found, negative 0.300 times 10 to the fifth. All right, and then our Kc value is coulombs constant, 8.99 times 10 to the ninth. All right, so we get 0.15 squared times our times a negative answer divided by 8.99 e to the ninth. And I got negative 7.51 times 10 to the minus 7th, and this would be charge and coulomb start with the same letter. Notice that we decided way back before when we drew this guy that it had a negative charge, and sure enough, when we did all our math, we found that we also had a negative charge here. So our answer here might be also given in microcoulombs, so it'd be like negative 0.751 microcoulombs. All right. So now what we need to be able to do is we need to be able to draw these as well. All right, we need to be able to represent these electric fields. And in order to do that, we're going to be using electric field lines. All right, and there's a couple rules that we need to know. All right, the lines must always begin on positive charges, okay, begin on positive charges or at infinity. So essentially what they're saying is they can never begin on negative charges. And they must always terminate on negative charges or in infinity. So they begin on positive or infinity and they end on negative or infinity. All right, essentially, then you can also think of this backwards and you can say to yourself, okay, that means I can never start on a negative and I can never end on a positive. All right. Second rule, so this is first rule. Second rule here says the number of lines drawn leaving a positive charge or approaching a negative charge is proportional to the magnitude of the charge. So essentially, if you've got two charges next to each other, all right, and you're drawing your electric field lines, the one that has more lines has the higher magnitude. All right, and then finally, I like to call this the Ghostbusters rule. Number 3, no two field lines from the same field can cross each other. All right, so if we were going to draw field lines to this guy, the way I like to think about this is what would a test charge do if we place it next to it. So if we put a test charge right here, okay, if we put a test charge right here, we know that it has a repulsive force, so it would get shot out this way. And so the path, the electric field lines, is essentially showing us the path that the test charge would take if we put them next to these other charges. So if we put a test charge right here, it'd shoot off straight off this way. Here it would shoot off straight off this way and like this, right? And we get something that looks like this one in yellow over here. Negatives would look very, very similar. Same lines here, or same rules, right? Always the same rules. I just repeated them right here. And then you can think to yourself, well, if I put a positive charge, test charge right here, okay, it's going to be dragged towards that because of the attractive force, and it's going to be dragged towards it. If I put it over there, it'll be dragged towards it if I put it over there. So these lines are the path, okay, that test charge will take. And so this picture right here that I'm kind of half covering up, all right, is this. Looks just exactly what we'd start to draw, only a little prettier. Okay. Oops. All right. So let's try it again over here. I'm just going to move myself up here to the corner. All right. So we're going to draw the electric field lines for these guys over here. All right. So it says apply the above rules and sketch the electric field around the charges combination. So we have to think to ourselves, what would happen if I put a test charge here? All right. So if I put a test charge right here where my pointer is, okay, we know that that test charge would be repulsed by the positive, and attracted towards the negative. So it would go across, straight across like that. Okay, that one's pretty easy. What if we put it right here? Well, it would start to get pushed away repulsively, but as it's coming along this way, oh my goodness, really, as it's coming along this way, it would also start to get attracted by the negative charge, and it would come out like this. Same thing here. If we put it here, it'd get repulsed at first, and then as it gets closer to that negative charge is going to start pulling harder and harder. We're going to be pulled off this way. Right? And then same thing here. This might be able to swing a little bit farther out, and then the negative will pull it back in like this, right? And then same thing down here, all right? And then, however, we say to ourselves, okay, well, what if we started over here? Well, the repulsive force will always be stronger, so no matter what, we'll just go straight away from that positive charge. And here, same sort of idea, it'll be straight away here. You know, we might do something like that. Okay, so on and so forth. All right, and then on this side, same idea, you know, something like this. So here is a better drawing of what would go on. All right, so we've got these lines here, and notice that they come off, shooting off the positive charge, and then they get dragged back in. All right, and so these would be the electric field lines for this set of charges. Okay. We can do the same thing with the positive, but these will only have repulsive forces. So if it'll shoot off straight away from this one like this, right? This line here, shoot off, this test charge would shoot off straight away from this guy. But as it's going, this charge over here would start to push against it this way. Okay, so when it comes out here, it actually come up here and get shot off like that. Same thing over here with this one, but remember they can't ever cross each other. All right, so it would get shot off like that, and then something like this, right, would do like that. All right, and then they kind of follow this pattern here. All right, so this would be what the electric field lines look for this guy. All right. Last little thing here is electrostatic equilibrium. Okay, electrostatic equilibrium occurs in conductors. All right, when there's no net motion of charges. All right, no net motion of charges. exists within the conductor. All right, so your charges are not moving. You've got some conductor, maybe a metal sphere, a wire, and the charges are not moving. All right. Now, the part of the trick is that your charges have to have the ability to move. They can't be fixed in place. And there's some ways we can do that. But in order to have electrostatic equilibrium, they cannot be moving, or they cannot be moving, but they have to have the ability to move. So they have to have freedom to move. All right, but they are not moving. All right, so for example, like if you establish, like if you have a positive and a positive here, and then you put a negative charge right in the middle of them with no forces pushing up and down, this electric charge here, this negative charge, has the freedom to move. It could move. We could grab it and move it, no big deal. All right, but because this force here attracting it this way is exactly counteracting this force pulling it this way, it's not moving. We would establish that as electrostatic equilibrium. All right, now because of electrostatic equilibrium, we get these 4 rules, and these guys are important, okay, because they'll kind of establish a lot of the rules that we need to rely on as we move forward, talking about more about electricity and circuits and how we can use them here. All right, so if you're at electrostatic equilibrium, all right, the electric field is 0 everywhere inside of your conductor. All right, so when you're inside of your conductor, your electric field is 0. All right, number 2. Any excess charge that's on an isolated conductor will always be on the conductor's outermost surface. And we talked about this when we talked about surface charges in the previous video, but this is just, again, establishing that idea. Number 3, the electric field just outside of a charged conductor is perpendicular to the conductor's surface. All right, so if you're looking at, and we've kind of already established this, and that makes sense, right? When you're drawing, if you have a sphere, all right, your charge is always on the outside, but when you draw your electric field, it's always going to be coming out, and this will always be perpendicular right when it comes out. And we saw this on this. When these guys, if we were going to draw this guy and where it attached, all right, this would have to be perpendicular. That's what it said. That's not my best, but all right. And then finally, on an irregularly shaped conductor, charge tends to accumulate where the radius of curvature of the object is smallest, or at sharp points. So say you've got, instead of a perfect metal sphere, you've got something that looks like this, okay? And then it's got a peak right there, all right? And really this is just an application of the 3rd rule, that the electric field resides on the conductor, is always perpendicular. Well, if we were going to draw perpendicular lines here, okay, our perpendicular lines, we'd have a lot more perpendicular lines right here at this point, infinitely many more, because this is a point in space right here at this point, so we can have infinite perpendicular lines coming off that point. So essentially, whenever you have a sharp point, you'll have an excess amount of charge. Okay, so make sure you know those 4 rules established because of electrostatic equilibrium in conductors. Super fun stuff, but not too terribly difficult. Especially this math that we did with the electric field is really important moving forward. Make sure you have a good grasp on electric fields, how we establish where they are, how they work, so on and so forth. All right, let me do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.